Welcome to Basics of Finite Element Analysis Part 2. In today's lecture, we will discuss a different type of quadrature known as Newton-Cotes quadrature, and we will also contrast it with Gaussian quadrature, and with that discussion we will close our coverage of numerical integration schemes. So, before we discuss this Newton-Cotes quadrature, let's see, let's very briefly recap the nature of quadrature points for Gaussian quadrature. So, we had said that if r is equal to 1, then my zetas, so these are values of zetas, then zeta is at 0. If r is equal to 2, then zeta is equal to plus minus 0.5773. If r equals 3, then zeta equals 0 and plus minus 0.7746. I am rounding off. If r is equal to 4, then it is equal to plus minus 0.339981 and plus minus 0.86111386. Now, if r is equal to 1, then this is the domain of the element minus 1 to 1, and my quadrature point is located at the center. If r equals 2, then again this is my minus 1, 1 and this 0, and my quadrature is located at, I have two quadrature points, it is located somewhere here, a little halfway mark between 0 and 1 and 0 and minus 1. If r equals 3, then I have, so this is minus 1, 1, 0, then I have one quadrature point located at center, and the other two quadrature points are fairly close to the ends. Okay. If r equals 4, so this is minus 1, 1, 0, two quadrature points are like this, plus minus 0.33, and then the other two quadrature points are fairly close to the extreme ends. So, the point what I am trying to say is that between the limits of 0 to minus 1, of minus 1 to 1, the quadrature points and these are also known as base points are not necessarily evenly spaced. This is one, and the second one is quadrature points may not be same as nodes for isoparametric formulation. The second point is valid only for isoparametric formulation. What does that mean? In isoparametric formulation, if r is equal to 2, there are 3 quadrature points, and also the number of nodes will be 3, and they may not be the same. The node will be at minus 1, 0 and 1, but the quadrature point may not be same. If the formulation is not, so that is there. So, these are the two important things to note. but this Gaussian quadrature gives fairly accurate answers, and it is performed in the zeta space, that is -1 to 1 space, and so it is very easy to automate. Now, there is another quadrature which is somewhat popular, but not as popular as Gauss quadrature, and that is known as NewtonCotes quadrature. So, that is known as NewtonCotes quadrature. So, let us look at this relation. Suppose I want to compute an integral of a function x a to x b, then if I have to use Newton-Cotes quadrature formula, then it is nothing but x b minus x a times the sum of this function, and this I evaluate at quadrature point t, tth quadrature, times this weight, tth weight, and t varies from 1 to r. T varies from 1 to r. Now, note that here we are still in x domain, we did not shift to the zeta domain. This is very important to understand. So, we are still in x domain. So, some important features are still in x domain. Second feature is these points, quadrature points, are evenly spaced. Third, first and last point are same as first and last nodes of the element. This was not true for the Gauss quadrature. This was not true for Gauss quadrature, but here first and last quad points are same as first and last nodes. So, so here spacing between points is equal to delta x, and this is equal to x b minus x a. So, suppose I have r points, then how many spaces we will have? R minus 1. If suppose there are r points, r quadrature points, then I will have r minus 1 intervals. So, divided by r minus 1, and we will through a table tell what these weights are. Okay. So, if you have an element, this is x a, this is x b, then you, if you have a lot of 5, 10 quadrature points, so like these are all quadrature points evenly spaced, and this is the spacing between two quadrature points, and this is equal to x b minus x a divided by r minus 1, where r is the number of quadrature points. So, next thing is that what are the values of weights. So, for that we will give you this table. So, you have this column r, and then you have weights W1, W2, W3, W4, W5, and so on and so forth. So, if r is equal to 1, then weight is 1. r is equal to 1, then weight is 1. If r is equal to 2, then weight is half and half. If r is equal to 3, then weight is 1 by 6, 4 by 6 and 1 by 6. If r is 4, then weight is 1 by 8, 3 by 8, 3 by 8 and 1 by 8. If r is 5, then it is 7 by 90, 32 by 90, 32 by 90, oh excuse me, 12 by 90, 12 by 90 and 7 by 90, and this should be 32. And so on and so forth. So, I can develop this table further down. Now, one important thing to note, a couple of important observations, that the case r is equal to true, r is equal to 2, this case, this is same as trapezoidal rule. Same as trapezoidal rule. And the case r is equal to 3, this is same as Simpson's rule. Okay. Another thing is that the error in the integration, error its order is directly proportional to the power of O to the its order is directly proportional to R. Okay. So, what does that mean? So, here I will construct another table. So, R can be 1, 2, 3, 4, 5, suppose. Then error order. Here the order of the error will be O to H. Here the order will be H square. Here the order will be H cube. Here the order will be H4. Here the order will be H5, and so on and so forth. Okay. So, what does that mean? That if H is small, right? So, this H is some normalized length, it is not exact, you know. So, it is normally non-dimensional thing, but what the point is that if H is small, then as I increase my R, things become more and more accurate, because if this H is normalized length. So, if if it is less than 1, then as R increases, I get more and more accurate solutions. And two more observations. One, if R is even, when is R even? That is, number of R corresponds to number of intervals. Or odd number of base points. Then formula is exact when f(x) is a polynomial of R plus 1th order or less. and if r is odd, then formula is exact when this degree. So, this I will erase, this is not correct. If r is odd, then this quadrature is exact for a polynomial of order r or less. Okay. So, these are two important things to note. So, this closes our discussion on quadratures and also today's lecture, and with this we close all the discussion on numerical integration schemes, and from tomorrow onwards, which is day 4 and day 5 and day 6, we will introduce new topic, which is how do we go around doing finite element analysis for two-dimensional problems which have a single variable. So, with that I close it for today, and we will meet tomorrow. Thank you very much.